Happy Friday, everyone. We have just completed taking a look at a couple of big topics with this new part of the course. One being how to find this thing we call the antiderivative, or we can call it the integral with all of its symbols and its procedures, and its uses to solve differential equations and even some physics problems. We then kind of move to a geometric understanding of what we're trying to do, and that is to approximate the area under the curve by just putting a bunch of rectangles either above or below the curve and adding the rectangular areas together. We also worked a little bit with some sigma or summation notation, which is really just a way to write those sums. Today what we're going to do is take a closer look and make a stronger connection between that thing we call the integral and that area under the curve. And first of all, if you read through the section 5.3, you're going to see this word, Riemann sums. Well, Riemann sums are basically what we have found. If you were ever asked to find a Riemann sum, it could be the upper sum, lower sum, or midpoint sum, or any other sum of a bunch of rectangles that approximate the area under the curve. And it is just an approximation. There's a lot in the problem set, or not so much the problem set, but the section, if you do the reading, that involves finding the exact area under the curve. That involves limits and really just a lot of manipulation. And we're not really required to do that, at least I'm not going to require it, so you can skip any of those types of problems that ask you to use the limit process to get the exact area. We'll have other ways to do that. But if I had 10 rectangles and then went to 20 and 40 and 100 and a million and eventually an infinite number of infinitely thin rectangles, I would have the exact area under the curve. So that's the concept of that limit process, but we're not required to do it. The big thing we want to look at in this problem set, in this section, is this thing called a definite integral. A definite integral is going to look a little bit different than a regular integral, and it's basically going to have a number kind of below the notation and above. I want to call them A and B. Sometimes we call these the limits of integration. It really doesn't have anything to do with the limit as we understand it. We just call the lower limit and the upper limit. But basically, this type of a notation means the area under the function between x equals a and x equals b. So for us, in other words, if I wanted to draw some function, that's my function, and it could continue, of course, and this is a, or b, let's say, and this is a. This notation represents this area. Well, that's a pretty cool connection, and there's a lot of calculus that would go into proving and showing that connection. Again, we're not going to be responsible for that, but that's really what it's about. So what we can do is we can now find certain areas under curves. But before I do that, let's look at some properties. Now, when I say properties, I'm talking about the properties of the definite integral itself. Some of these, at least most of these, I hope are rather intuitive. For example, what would we say that the integral from a to a would be of a function? Well, I would hope you'd realize that if I go from a to a, there is no area. So that's pretty simple. Here's another one. If I take the integral from a to b, and to compare it, the integral from b to a, I am going to state that they are just the opposite of each other, because the definite integral is going to be a number that represents the area. So the area from a to b, in this case, would be a positive number. If I want to go from b to a, it would be that same area, but the negative of that area. Next, let's kind of break it up into pieces. If I pick some value c, I don't care where it's at, pick some value c, doesn't have to be between a and b, even though it's nice when it is. hopefully it makes sense that if I take the integral from a to c and add the integral from c to b, I'm going to get the integral from a to b, because it's one area plus another area would equal the final one. So those are some nice properties. And here's probably the last one. If I have an integral of some constant times a function, that of course can be written as that constant times the integral of the function. So if you understand what a definite integral means in terms of a picture, hopefully these properties are rather intuitive. Okay, now let's take a look at some examples of how this all plays out. And first one. Let's say I want to evaluate the integral of 4 from 1 to 3. Well, the integral of 4 from 1 to 3 would just be basically the area underneath the function 4. The function 4 is nothing more than a vertical or a horizontal line. So what we're looking for is basically this. It's not too hard to figure out that if that area is just going to be 2 times 4, so that definite integral has a value of 8. Not much to it. What about x plus 2 from 0 to 3? If we are asked to evaluate this function, same idea. Let's go ahead and get a picture. X plus 2 from 0 to 3 would be here at 2. At 3, it's going to be up here at 5. So the value of that integral is basically going to be the area of this figure. Well, this is a trapezoid. The area of a trapezoid is going to be 1/2 the sum of the bases. The bases are 2 and 5, so that's 7 times the height, and the height is 2. So we're going to get 7. Now, of course, you could break this up into a rectangle and a triangle. Really, however you want to go about it's fine, not a big deal. Let's look at another one. What about the integral from -2 to 2 of the square root of 4 minus x squared? Well, again, we need to sketch what radical 4 minus x squared is. And hopefully by now, many of you are realizing, seen it enough, it's a semicircle. So it's going to have a radius of 2. So it's really just the top half of a circle. Not too bad. So what I'm looking for this integral is going to be that area. Well, of course, it's just going to be 1/2 the full area of the circle. And the circle is going to be pi r squared. Simplify that, hopefully you get 2 pi. So I have evaluated definite integrals only because I recognized the geometric shape that the function created based on those limits of integration. Now I'm hoping you're having this question, that what if these functions are not so nice? Well, then we've got another issue, and that's something we'll look at really later next week. But if you are expected to evaluate a definite integral, you're either going to be given enough information about the little pieces of the area, or you're going to be able to graph it, and you're going to be able to understand and recognize it as a geometric shape. Now, there is a problem number 60 in the text, and I'm going to want you to look at it. But number 60, as an example, asks us to integrate log of x from 1 to 2. Well, again, if I would look at a picture, the log of x looks like this. So from 1 to 2, the log of x would be this region. Okay? And we happen to know that this value right here is going to be log 2. Okay? Now, this problem is a multiple choice problem. So here are our choices. We have 1/3, 1, 4, or 3. So is it 1/3, 1, 4, or 3? So only because we know what it means in terms of area, there's no way it's going to be these two. Because think of this as a rectangle. That's going to be 1. This height, log 2, is basically less than 1. So that's less than 1. So the only one that's going to work would be 1/3. So that's going to be the lesson. There are many other problems in the problem set. So good luck with it. There's not going to be a lot of calculation. It's mainly understanding that the integral is the area under the curve. There are a lot of properties. There are many problems in the problem set that force you to kind of understand these properties. Now, as we look ahead, here's something that's important to remember. If you look on the schedule, middle of next week, you'll be given some type of a take-home quiz. So we really have several days to work through problem sets 5.1, 5.2, and 5.3. If by Monday, you can maybe send me a list of problems that you're struggling with, I can put together a little review, a video, or a couple of them on Tuesday. Many times, if you do have questions, I'll first try to talk you through it on an email because I think that can be very beneficial. But if you would like to see me actually do the work and show you the step-by-step procedures of certain problems, I'd be happy to do that. So throughout the weekend, continue working on 5.1 through 5.3. Let me know if you have any issues or problems over anything. And as a reminder, thank you for turning in the worksheets. I will say in future reference, just make sure the pictures, if you're using pictures, are very clear so I can read them. Sometimes scanning can be more helpful and more clear. But again, whatever your technology allows you to do, I will accept and work through it. So have a good weekend, and we'll talk to you next week.